Hi, today we're going to take a look at simultaneously probably one of my favorite lessons of the year and then also one of my least favorite, organic reactions. I've said this before, there's a whole course devoted to just organic reactions. Two courses actually I took in college, so a full year of study. And we're going to get through this in not quite that long. But just to get started, I have a video for you to watch. Again, we're going to take notes. Write down any questions that you have as we're watching the video. I don't think there's any sound included, but 2 minutes should be good. That is interesting and kind of gross at the same time. I don't know if you're going to make the same face I make when watching this. Oh, keep playing. Keep playing. So as they spin the rod, it's like pulling on this thread, but then if you look on the bottom, like as it pulls the thread, it keeps forming, I guess. It keeps pulling. But it makes meters of this, and it's a thread. I mean, hopefully you've heard of the term nylon before. That's really the thing to focus on. So that's kind of like one thread. I now know how I can become Spider-Man. Kind of. So I've actually got like several videos about nylon in specific, because there are a bunch of people on YouTube who've either uploaded a video or created a video about it. But nylon, so a couple of things I want to pull out of here. First off, why does the reaction keep going? What's with the condensation? What is nylon? What is sebaceous chloride? What is 1,6-diaminohexane? They said nylon 610. So like there's all sorts of things to pick out of this. And like I said, I really do enjoy talking about organic reactions, but since we're only really spending one day on it, I don't want to get too deep into it. Here's what I do know. They named one of the compounds as 1,6-diaminohexane. First off, that's not in line with how we name our amines. I believe it would be 1,6-hexane diamine would be how we would name it. But that's probably where the 6 comes from in the nylon 610, so then we can conclude that the sebaceous chloride provides the 10. There's also nylon 6,6 and nylon 6, and there's like I said, I'm going to provide a bunch of links at the bottom of this so you can keep watching videos. But really, the big question I have is, how do these, I'm assuming this is an organic compound, just because, I'm showing it to you today, but how do these organic compounds interact with each other? And it turns out that there are, I think, 7 different classes of organic reactions that we're responsible for going through together. And so I'm just going to try and go through them like I said, as quickly as possible. The first one, you're already familiar with, combustion. In general, a hydrocarbon reacts with oxygen to make carbon dioxide and water. And of course, this is our unbalanced reaction because it's the general reaction. In specific, we have the combustion of propane here. It is possible to have what we would call an incomplete combustion because you're seeing that we're making carbon monoxide. There's also an incomplete combustion that we've seen a lot in lab where you have a yellow flame and you're actually leaving behind carbon. And in each case, what you can see is that this is a 1:5 ratio of hydrocarbon fuel to oxygen. This is a 1 to 3.5. So like not having enough oxygen is yielding that incomplete combustion. But we're just gonna keep moving on. Oh, I forgot to find an image. I'm gonna have to link an image, but we'll get to that in a second. There are two different reactions that have to do with just hydrocarbons and how they interact with halogens, and they're called addition and substitution. So what we have on the bottom here is a test for whether or not a hydrocarbon is unsaturated. I'm going to play it and then we'll talk about it.
The tube on the left contains the saturated hydrocarbon cyclohexane. The tube on the right contains the unsaturated hydrocarbon cyclohexene. First, brown-red bromine is added drop by drop to the left-hand tube containing saturated hydrocarbon. As the bromine is added, it dissolves in the cyclohexane. The color remains when the solution is stirred because bromine does not react with saturated hydrocarbon. Now, liquid bromine is added to the unsaturated hydrocarbon cyclohexene. The red-brown color disappears as the bromine mixes with the cyclohexene. This is because the bromine reacts with cyclohexene, adding to the double bond.
All right then.
This reaction is a very convenient test for the presence of a double bond in a molecule.
Well, there you go. That's everything. So, like it said in the video, addition is when you incorporate a substance into your hydrocarbon, and substitution is not in the video, so we'll talk about that second. But what we have here is she mentioned cyclohexane and cyclohexene. We haven't talked about cyclic hydrocarbons, but hopefully you can gather from the names is that by the ending, one of these is an alkane and one of these is an alkene in terms of its structure. And so for the sake of argument, I found two examples using ethane and ethene, a little bit easier to conceptualize the picture. In the case of ethene, what happens is when we react ethene with a hydrocarbon, you saw in the video that there was actually a reaction. It's weird because the reaction is that the color stayed colorless, but what that meant was you added a brown-red bromine to it, and the bromine changed color to colorless. But if we were to draw out some structures, what we would have for your ethene would be this. And if we added chlorine or bromine to that, what they're telling us is we actually get this. And the way this reaction works in an addition is that this double bond gets broken open and the two chlorines kind of fall in to take those open spaces that are created. So in a way, the addition reaction is kind of like what we saw with a synthesis reaction where two reactants become one product. In this case, what we would have made here is a 1,2-dichloroethane. And the biggest thing to note about an addition reaction is that it actually increases your saturation level. An alkene would become an alkane, an alkyne would become an alkene, would become an alkane. And so this is a way of saturating your hydrocarbons. In fact, there are ways to add hydrogen to an unsaturated hydrocarbon to make a saturated hydrocarbon. This process would be called hydrogenation. In the substitution reaction, what we have is a little bit different because we're already starting with a saturated hydrocarbon. The presence of the chlorine... Oh, now I need the eraser. Oh my god, the eraser's covered. I really hope the buttons... Uh-oh. I'm going to have to figure something out with that. I'll just cross it out for now. note to self, don't put videos in the bottom left-hand corner, because then the controls go away. What happens is, since there's nothing to add into, actually what will happen in a substitution reaction, and I don't have a good video for this because no one's recorded one, you usually need something to get the reaction going. In this case, UV light with its high energy would actually cause, I'm going to stop saying actually, would cause the halogen bond to break, and you would create a radical and a single unbonded electron. And what ends up happening is that the same would happen as the one electron here kind of goes over and goes after the hydrogen of your saturated hydrocarbon. And so your end products would look something like this, where a chlorine atom ends up attached and you create an HCl molecule. Now this is not an acid, because this is all being carried out in a non-aqueous system. So the gas that's made it's a gas, it's not an acid. But the big difference here is this looks like a single replacement. And yes, it's possible to do a substitution with an unsaturated hydrocarbon, and like I said earlier, this all branches out into several reactions. Each of these you could take a lot of time to just dive into, but I'm just kind of giving you the surface. So addition and substitution. Esterification. So this is where I would definitely include a picture. I'm going to include some links to a picture that's kind of helpful. Esters, in general, what we're going to say is this is an acid, of course, because it says acid, and an alcohol. When they react, they're going to react in the presence of acid. Typically, I think there might be a base catalyzed version, but I've always known of the acid catalyzed version, to create water and ester. And that's why they call it esterification. Creation of an ester. And esters are characterized by their smell. In general, esters have pleasant smells. These are the floral, the fruity scents. A lot of times when you eat food and it says artificial and natural flavors added, well, if there's ever an artificially created flavor or odor, most times it's an ester in some way. And the way you can identify an ester is this C double bond O, bond C in the middle of your compound. Now this example is not the greatest to really see what's happening here, but now that I have my controls back, let me erase this. And I'm going to start to bring in a couple of colors because I think this should really help. What you end up seeing is, if we look really closely, this C double bond O is our anchor point for looking at the ester in terms of where it came from. And like I said, I'll record some more videos to go more deeply into this. But these two carbons end up here, and these two carbons end up here. And note that the big difference is the carbon with the double bond O, otherwise known as the carbonyl, ends up there. And that kind of helps our anchor point. Now, this example is not great because it's two carbon acid reacting with a 2 carbon alcohol. So of course, both sides of your ester have 2 carbons. But a better question would be, what happens when, say, you have like a butanoic acid reacting with methanol. And of course, don't forget, when we write alcohols, you want to be careful. Since the carbon is in fact bonded to the oxygen, you want to write your alcohol the other way around, an HO instead of an OH. In this case, we have this water that's created, and you can see a bunch of H's and O's in the middle here, and I left them out of my drawing on purpose. The water that's created gets created with these 3 atoms here, and so then your carbon-oxygen bond gets formed between these 2 atoms. So what we end up with is, I'm going to change my colors again, your butanoic acid. This is your butanoic acid part. And this is your methanol part. And of course I picked red and green because I like to punish myself clearly. But in terms of the naming, just to point out, there is an example on table R that you can go look at, but the alcohol gets named as a side chain. So this would be methyl butanoate. And I don't remember what methyl butanoate smells like. There are a couple of examples where you can make wintergreen is methyl salicylate. Isoamyl ethanoate, I think, is the fake banana, but it's not even the fake banana. There's a whole story behind that. Not going to get into it, but that's really how that works out. And then, of course, don't forget to make a balanced reaction, you need your water as well. Kind of the opposite of esterification is something called saponification. And the big way to identify saponification is that a soap is made. Notice this. This is a fat. And a fat is characterized, I mentioned a couple videos ago, by these long carbon chains. 17 carbons off of each of these. But there's a link between each of those fatty acids and the rest of the molecule, and that's an ester link. So really, a fat is just a fatty ester, or an ester of fatty acids. And to react the esters away, we use strong base, sodium hydroxide. What you end up with is this glycerol, sometimes called glycerin. If you've had any in your soap, usually makes your skin really soft. And then we have our soaps over here, and this bond is ionic, just to not be confusing with it. So a fat plus a base makes glycerol plus your soap. And the way the soap works is you have this big long chain of 17 carbons, and then you have this double bond O, and that's got a negative charge. So just first to be clear, what we have is this is kind of the opposite of esterification, because we take our ester, we react it with base, and what we get here is an alcohol, and then this is the conjugate base of an acid. This looks like an acid that has a sodium instead of an H. And when that acid is missing that H, what happens here is this is charged, so that would be polar, and this is hydrocarbon-like, which is nonpolar. And that's what really makes soaps work. The idea behind soaps is that this nonpolar bit, if you had like a glob of fat or oil or dirt, this nonpolar bit, all these tails that are not negatively charged would sink into this little bit, and then you'd have all these negative charges that don't really sink into it on the outside, but these negative charges have the ability to interact with your polar water. So when you introduce soap to oil and water, the non-polar parts of the soap get into the oil and polar parts of the water get into the soap, and you make these little balls of oil that have these little negative charges sticking out of them, which helps the water dissolve them. And that's basically how soap works. Moving right along, we have something called fermentation. Fermentation, the general form is sugar will create alcohol plus carbon dioxide. Usually fermentation, every time. Yeast, bacteria needed to carry it out. This is a non-oxygenated environment. You'll see that oxygen's not a reactant. So this happens more likely in an anaerobic fashion, and usually this process, the alcohol that's made serves a function. Alcohol, of course, this is your ethanol, the kind that we can drink and creates all sorts of effects, the social alcohol, but there's plenty of other alcohols that exist. But in general, the alcohols are antiseptic. I mean, they kill microorganisms, which would be good If you make a little bit of it, if you have like your yeast or bacteria colony, it helps kill other things that are present, letting the yeast or bacteria survive. Maybe they're better able to handle it. Sometimes the yeast or bacteria create so much alcohol that they kind of kill themselves, but don't want to get too far into that. But this is why in early human history, drinking just water isn't great. A lot of early cultures, I know this is true in like the Middle Ages, beer was safer to drink than water because the alcohol content of beer helped ensure that there wasn't anything growing in it. If you just went into a lake and just scooped up some water and drank it, there's all sorts of things living in there. And so the beer was actually cleaner. Now we have water treatment, which helps. This is something I wanted to mention. It's along the pathway. The alcohol ends up turning into, if you let it sit out too long and does get exposed to oxygen, it would become an aldehyde and then eventually an acid. So I don't know if anyone's had firsthand experience with this, but this happens to wine, where if you open the bottle and you drink some wine and you put the cap on the bottle and you let it sit for a while, oxygen has gotten into the bottle. You open it again, you have a little bit more, you close it up. And eventually, if you do that over a long period of time, the wine starts to taste a little sour. Well, that's because the alcohols, when you expose them to oxygen, will slowly react with the oxygen. Oxygen is a very reactive molecule, and you will make aldehydes, and then you will make acids from that. So this is our organic definition of oxidation. Instead of talking about gaining or losing electrons, typically with organic molecules, we say it gets more bonded to oxygen. So in the alcohol, you have one bond to an oxygen. In the aldehyde, you have two bonds through the double bond. And in the acid, you actually have three because it's two to the double bond and one to an additional oxygen. So as oxygen gets more incorporated, that keeps happening. You don't really get oxidation beyond the acid because I think what you then have is like free carbon dioxide or something like that. Moving right along, I think we're almost done. We can now come back to the video that we saw. The last reaction is polymerization. And in polymerization, we can pick apart the word. Polymer is a large organic molecule made up of repeated units, known as monomers. So polymer is many mers. I think mer means like unit, like isomer. Same unit. Same something. I can never remember what mer means. It's from some language, Latin or Greek or something. If anyone knows, please let me know. But there are two types, and the nylon is definitely the second type, the condensation, but I just wanted to show both reactions. So what we have here is like two ethyne molecules, or sorry, not two. Many ethyne molecules can react to make one long chain of repeating ethene molecules over and over and over and over and over again. And it would happen like, say, n times. So what this is saying is n small particles become one large particle of length n. And I don't really want to go into the mechanisms. If you guys are interested, let me know, and I can record something additional. But that process is either radical-based through an unpaired electron, cation-based, or anion-based. You have to initiate it usually. But the condensation one, it yields much more discussion. Condensation because it creates water as a product. And then you can see that the water missing creates a bond right there. I realize this says amino acid, and then this would be called a dipeptide. So working a little bit of biochemistry into there. A protein or an enzyme is actually an example of a polymer. The repeated units are not all the same unit, obviously, but it's made up of the same 22 building blocks. It's just a bunch of amino acids, and it's only those amino acids that go into it. And so what you can say is like that's actually an example of an organic of a biological polymer. There are plenty of non-biological polymers. So we can say proteins and enzymes are biotic? Yeah, maybe that's the right word. And the name for an abiotic polymer is plastic. So in the lab, if you wanted to make polymers, you're basically making plastic. And polymers are named by naming that monomer unit, and then you put the term poly in front of it. So if you've heard names like polyester, polycarbonate, polyethylene, polystyrene, each of those are plastics, and then those are built up of that same repeated unit. And then to give you guys a bit of a summary of just how the polymerization works, I have the reaction down here between adipic acid becoming adipoyl chloride reacting with the 1,6-hexamethylene diamine. IUPAC rules. They take the acid and the chloride and they react them in such a way that when you make this, what is kind of interesting, I'm going to switch colors to make my point before I play the video. What is kind of interesting is that when you make your product, you still have an amino group and an acid group. And so the amine group of the dipeptide can react with another amino acid. So you will see in these polymerization reactions that the types of molecules that are used are such that once the reaction occurs, the product is allowed to become a reactant in another reaction. And that's how you get these big long chains happening. But I'm going to let NileRed do some talking. I'll link the video below, of course. But
this video is sponsored by Audible. Nylon is an extremely important family of polymers that can be used to make a huge range of different products.
I'm going to have to include it. But you know what? I might just include a link to it. But he explains things so nicely.
Into plastic parts and tools.
That's a shame.
Nylon was first...
I screwed up. I meant to... I was hoping I could full screen it in the PowerPoint. That's fine. I'll link it below so you guys can watch because it's a long video. I wanted to play. He goes very well into how it happens. And I think that's where I need to end things. These reactions exist. And there are a lot. We covered, I think, 7 total. There are a host more. Aldol condensations, ring opening, metathesis polymerizations, what's the metal? Grignard reagents, Geldol condensations. There's all sorts of Fischer reagents. You know, actually, the esterification is known as a Fischer esterification that we saw, but we're not gonna go through the mechanism. But while they are varied and numerous, you're responsible for knowing those and go back and look at them. How they work. Really has to do with the chemical properties of reactants. And when I say reactants, let me see if I can, there you go. Nope, too many, that's fine. Of the reactants. So you really were looking at things like, is there an acid? Does that mean that you can lose an H+, and will that cause a reaction to happen? Is there a C double bond O? Because that means that C is pretty positive, because that's a really polar bond, and that O is really negative, and can that push a reaction? And so really each of these reactions exploits some property like that. But in terms of any through-line summary of each of those, because they're all so different, I would just say, if you're curious about one, go do some research, go do some digging, because there's a whole world there for you to see. Thanks for watching.